Welcome to the 23rd Recitation Zero about DataParallel. If you follow the news around the world about artificial intelligence and deep learning, uh, you know that one of the main issues, even for big tech, is about having enough compute to train models and use these models to infer. And one of the ways to address this issue is by having better uh, devices and also by using many of those high quality devices to distribute the compute uh, requirements around these machines and shorten the time required for training and inference. I'll be guiding you through DataParallel, which is the most basic class in PyTorch that supports distributing the training around uh, multiple GPUs, and I'll be guiding you through how to use DataParallel, how to train a model using DataParallel, and how to save a model trained by DataParallel. For starters, I will first import PyTorch to see if we can use DataParallel. We would have to have multiple GPUs. In this case, I'm using an instance of Kaggle kernel that has multiple GPUs. And as you can see, we are using PyTorch 2.6.0 and having two GPUs, two T4 GPUs, as you can see from this widget. The main thing about DataParallel is that and how DataParallel works is when having a batch, the data is sharded into all of the GPUs, and that means when setting the batch size using DataParallel, we need the batch size to be larger than or equal to the number of GPUs available, so that it can be distributed around those GPUs. Since we shard this batch into the different GPUs, and one of the most important thing about DataParallel is that we need to set a primary GPU that we will copy the model from during the epochs, and also we will compute the gradients using this primary GPU. So the batch is sharded into, in this case, four different mini batches, and then these mini batches are sent to the GPUs. The model weights are also copied inside all of these four GPUs. We will calculate the gradients in all of them. We will, after doing the forward and backward propagation for the grade to calculate the gradients, we will send those gradients to a shared memory. We will sum them and do the weights update inside the primary GPU, and then we will send the model weights through this shared memory. It's most importantly noted that this parallelism approach is done in a single process across multiple threads, with each thread being dedicated for each GPU, for one GPU. The process is then repeated for each epoch. We will copy the weights of the model to the GPUs. We will send the shards of the batches. We will calculate the gradients. We will sum the gradients inside the primary GPU, and then we will update the model weights inside the primary GPU first, and then send it to the secondary GPUs. Here we will define a simple model. The model we are using is just 2 layers, and the dataset that we will be using to train this model is a synthesized dataset that we will be creating later on in this notebook. We will define the class of the simple model. We will do some configuration to initialize the model with some input size and some output size, and also we'll declare the batch size and other stuff later on. Here we are synthesizing the data. The input size is 784 like points for the data or columns, and the output size is 10. And here we are synthesizing data for 10 classes. The batch size is 256. We will later on print the batch size outside the model and inside the model. And these are hyperparameters for learning rate and the number of epochs used to train the model. Here we generate the input and the output for the model. We will create a simple dataset using Torch tensor dataset, and then we will create the data loader using the dataset synthesized dataset. Here, if we have multiple GPUs, we will need to wrap the model using DataParallel. We declare the model. We check if we have more than one GPU. And if we have more than one GPU, we will wrap the model using DataParallel. And else, we just print that we do not need the DataParallel, and we are either using one GPU or CPU. So after wrapping the model using DataParallel, we need to send the model into a device, and that device that we send the model to is considered the primary device by DataParallel. After sending the model to DataParallel, all of the procedures or the steps we will be doing is just the same steps used to train as a model in PyTorch. We will declare the loss and the optimizer, and then we will look into the training loop. If you see here, for the first batch of the first epoch, we will be printing the batch size or the batch dimensions in general outside the model. And if you see here in the simple model declaration, we print the batch size that is passed into the model to compare it to the batch outside the model. So this is like typical steps in PyTorch training. We get the input and the target. Here we just use it for debugging to print the batch dimensions. We pass the batch into the model. We get the outputs, and then we calculate the loss. We zero out the gradients from previous batches, and then we calculate the gradients, and we update the weights. And then to check the model performance, we are also calculating the total loss. When we execute this training, as you can see, outside the model, the batch size is just the same batch size we declared, which is 256. And inside the model, since we have two GPUs, the batch size will be divided into two shards, with each shard having 128 data points. And the training is just almost the same as PyTorch training. And finally, we will see how to save the model, a model that is trained by DataParallel. If the model is an instance of DataParallel, meaning the model is wrapped using DataParallel, we can get the weights or the model uh, by getting the attribute module, and then we can use it using like how to save a model in general in PyTorch. We get the state dictionary and use it and save it using torch.save, and then we specify the path. And to load the model, after that, we will just initialize the model and load these weights into the state dictionary of the model, and then wrap the model around data parallel. This is the data parallel recitation 0. I hope you get the chance to play around with this notebook. I am Ahmed Al Hassan, and thank you for listening and following me through this notebook.